All right, so the first thing I'll draw your attention to is the assignment. So it's posted. So assignment 1 will be due in 2 weeks. You'll upload it. We're going to try and do it just through Moodle itself, so you can submit assignments apparently through Moodle. We've never done it before. We used to use a system called EAS, but now you need to either be at Concordia to use it or you have to VPN in, and it was a headache for students to use last term. So we're going to try and switch to Moodle. So it's not on Moodle yet, but by next week I'll have it. I'll go through how to do it on Moodle itself, but you don't have to worry about that. Okay, so what I'll do is all students will have slip days, which they can use to hand in an assignment late. You can choose yourself. If you want to use your slip day for assignment 1, you can hand it in late, but then assignment 2 has to be on time. Or if you want to if you hand in assignment 1 on time, then you might as well slip on assignment 2, okay? So to use the slip day, it just lets you hand it in on Friday instead of Wednesday, so it gives you about 2 extra days. You don't have to tell me, don't send me an email or anything, just hand it in late. We'll keep track of who's late on assignment 1 and on assignment 2. So you can't use it on both assignments, but you can use it per your choice, and you don't have to tell me about it, just do it, just hand it in late, okay? If it's like 5 minutes late or 10 minutes late, like it doesn't matter at all, okay? So like we're not there like checking the exact time stamps and things like that. Just get it in around the deadline. If you have like an actual medical reason, like this is just like, you don't have to give me an excuse, you just do it. But if you have like some other reason why it's late, then just email me and we can accommodate all of that type of stuff anyways as well, okay? The assignments, both of them will be just a document. So it will be in PDF format. You can write it in Word or whatever, however you want. And it's helpful when we mark them if you follow this naming convention for the file itself. Okay, before we get to the assignment itself, is there any questions on that logistics of it? Okay, so the assignment, I'll let you read it. I'm not going to go through it line by line. But basically, what I want you to do is look at STRIDE and evaluation frameworks. So what I did is I came up with different methods that you might use if you are selling concert tickets. It could be a sporting event, doesn't really matter. But like say you're a venue and you know there's a concert and you want to sell tickets to it, okay? And there's a couple of constraints that you might have. So artists don't like it when people scalp their tickets. So they buy them all up in 1 minute, and then they turn around and they sell it for 4 times the amount. Okay. So if you can limit the number of tickets that people can have, how fast they can buy them, things like that, that's something that's useful. Another thing that happens a lot is there's a lot of scams. So you'll go on StubHub, you'll buy a ticket, you'll get the ticket, it looks real. But then when you show up to the venue, they're like, oh, sorry, someone's already sitting in your seat or something like that, okay? So like, how do you know it's real? How do you know it's your ticket? Especially, like if you buy it directly, that's fine. But if you buy it from a second person, how do you know they didn't print out 10 of them and sell all 10 of them? Okay, so anyway, there's different security considerations that are involved. Yeah, I forgot my bag, thank you. Okay, so what you'll do is I suggest 3 systems, and so you can look at the 3 of them. They all work a little different. Some of them would involve like online databases. Some of them would be purely offline. Some of them have names and identity. Some of them it's just like whoever has the ticket. Okay, so these are 3 different ways that you might implement it. So you can read the description of them. There might be things that you want to assume that's not captured. Like the description is just 4 or 5 sentences, so it's not going to cover everything, okay? So if you need to make an assumption in order to analyze the system, that's fine. That's part of the assignment. So just write down what your assumption is, and as long as it's reasonable, it's fine. The TA will account for it, okay? So in terms of the assignment itself, what you'll do is, first off, you'll just go through STRIDE. So you start with spoofing. And what you'll do for spoofing is you'll take the first system, which is the physical ticket system. And you're going to tell me, is spoofing relevant or not? Okay, maybe you decide there's no spoofing attacks anyways, okay? But you're just going to say, okay, yeah, spoofing is a problem here or it's not a problem here. Then you'll say for physical tickets, how does it do on, like, what does it do to try and combat the spoofing attacks that you have in mind? And is it good enough or is it not good enough? So you might say, well, maybe someone prints out fake tickets, but there's no real way to stop it, right? So then you'd say, well, it's kind of bad on spoofing for that result or whatever, okay? Then you'll spend another couple sentences talking about the other two systems, and you might decide they're exactly the same. It's no different. All ticketing systems have the same problems. Or you might say, hey, this e-ticketing system, you know, it has these digital signatures, and that really solves the spoofing problem, whereas the other one doesn't. Whatever, okay? So you'll spend another couple sentences. And the reason that we're limiting the number of sentences is from the TA's perspective, they're going to get 100 of these assignments, and it adds up. It's, you know, if everyone's assignment is 4 pages times 100, that's 400 pages of stuff that they have to read, okay? So everything is sort of like limited. If you go over one time with one sentence, do we care? No. Are we going to sit there and count sentences? No. But I'm just trying to make it easy for the TA to mark, okay? So anyways, you'll do that for spoofing. So a couple sentences about what are the spoofing attacks, a couple sentences about how physical tickets do or do not address them, and then a couple sentences about any differences between the other systems. Then you'll do the same thing for tampering. You'll do the same thing for repudiation, information disclosure, denial of service, and escalation of privilege. Okay, so that's the first question. And then the second question is gearing you up to do an evaluation framework. Okay, so evaluation framework would be you want to compare these three. So you're going to have a bunch of columns. You're going to have the rows are given to you. They're these three systems, and then you're going to evaluate them. Okay, so the first thing that you'll do is you'll basically just come up with your columns. Okay, so we want 6 security columns, and you should say what the security property is. What does it mean to get a full dot, a half dot? If you want to use half dots, you don't have to. And what does it mean to get no dot? And then you'll repeat it for usability and you'll repeat it for deployability, okay? So just what the columns are in terms of the criteria, okay? And then just to save time, you don't have to do the full chart. So you don't have to do the full chart for all 3 systems. What you'll do is you'll do just one of the systems. So online system is the third. So you'll take that as the representative system, and then you'll actually give it the dots all the way across that particular row, and then you should say why are you giving it a full dot or why are you giving it a half dot or that type of thing. So everything needs to be justified. Okay, and the columns themselves, you can, if there's some from that passwords paper that sound relevant, like easy to use or whatever, like you can use them. At the same time, tickets aren't passwords. They're a different problem. And so I would expect that some of your columns are going to be different from the other ones, okay? So I'm not saying you should use those columns. You shouldn't use those columns. But if there are columns that are applicable to both, you're free to use them as well, okay? So that's not a problem. I put in a couple other evaluation frameworks from my papers and other people's papers that you might get ideas for columns or what it looks like in terms of the write-up and things like that. Okay, so a lot of you will come up with more or less the same thing, but there's going to be a lot of differences, right? Everyone will have slightly different columns or different things that you emphasize. The security criteria, also you can use part 1, like the stuff that you came up with in the stride part, you can turn them into columns for the second part. But anyways, that's basically the assignment. I hope it's pretty straightforward. Every year this is new, like the ticketing idea. We did COVID passwords last year. But it's the same kind of template of an assignment. It's just like the things that you compare differ, and students don't seem to have a problem with it. It's just a matter of time of like just sitting down. And sometimes you struggle, like you have 4 good security properties, or deployability tends to be a little harder, or maybe usability, and you're struggling to get a 5th or a 6th. So I am going to insist that you should be able to come up with 6 for everything. Okay, but yeah, that's it. Okay, is there questions about it? Yeah, so you can use any, yeah, so the chart itself, the rest of it, it will be just bullet points up to question 4. So question 3 will just be like, this is the security one and this is what it means. And then for question 4, you can do it one of 2 ways. You can, I would like the chart to be in the document itself, not a separate thing. So you can just make a table in Word. Or because you're just doing a row, you can even do it in bullet point. You can just say column, I'm getting a full dot, and then this is the reason. So it can just be sentence space. It doesn't, you don't have to graphically create the chart if you don't want to. If you were doing it like with all, like the complete chart, then you want it in graphical form so you can easily compare. But for the purposes of the assignment, you don't even have to put it in graphical form. It can just be a list. Okay, other questions? Okay, so this is due in 2 weeks. So next week you also have a chance to ask questions. So take a week, look at it this week, try and, even if you're not going to do it this week, at least read through it. And if things don't make sense, there could be bugs too, like maybe I didn't explain things very well, and I'll update it as a result. But yeah, at least start thinking about it. It's coming in 2 weeks, and I hope it doesn't take like a super long amount of time, but it's mainly just to get you doing it, and you'll realize it looks easy. Like when I did it in class, it looked easy, but when you have to do it yourself, it's a lot harder to come up with these things. Okay, is there any questions about anything else, like the lecture from last class or anything? Okay, so seeing none, we'll move on to the main topic. Okay, all right, so we're going to move to a third sort of high-level methodology, and then we're done. So we looked at STRIDE, we looked at evaluation frameworks. Now we're going to look at something called attack trees. And attack trees, unlike the other ones, we did them pretty quick. This one we're going to take our time. So this could take, it's 200 slides, so it's probably going to take 2 classes. It might take 3 classes to get through it, but we're going to go in a lot of detail. And it shows you that just because it's a high-level methodology, it doesn't mean you can't dump a lot of detail into it if you're able to do it. Okay. So the example that we're going to use to illustrate it will be HTTPS. I'll tell you what that is, but it's like the lock that appears beside website names when you go and visit websites. And we're going to think about how that lock works and why does it appear and how can you attack it? Is it actually secure? Okay, so attack trees are they're still a high-level methodology, so you can use them for anything. You can use it for software, protocol, hardware, they're pretty general. But as you'll see, you have the potential to do it in a very detailed way if you want to spend a lot of time doing it. So evaluation frameworks is sort of like you're studying a lot of you're comparing multiple solutions to each other. STRIDE, you're just looking in detail at one solution. And then with an attack tree, it's even more narrow. What you're looking at is you're looking at one attack on one system, okay? And it's not so much an attack, it's more like what the adversary wants to do. So the attack is how they end up doing it. But like, what's the goal of the adversary? That's what it's centered on. And then you're going to try and brainstorm basically every possible way the adversary might achieve that goal. And part of the idea of an attack tree is to show that there's more than one way of doing it, okay? It doesn't matter at the end of the day if you beat the system, it doesn't matter how you did it. As long as you found one path through that led to an attack, then the adversary achieves their goal. Okay, so what you're going to do is you're going to basically brainstorm what are all the possible ways we could break the system. You can include both what we call, sometimes we distinguish between threats and attacks. So an attack is like something that actually happened, and a threat is more like a hypothetical, like in theory you could attack it this way, but maybe it doesn't work or whatever. No one's shown that it works for sure. So attack trees are more properly, everyone uses the term attack tree, but it's more like a threat tree. Okay, so you're supposed to include threats as well. It doesn't have to just include attacks that actually happen. It can include threats or like ways that you might go about the attack, whether it actually works or not. But it has to be plausible, like a realistic threat. And then you can use Stride to help you do the attack tree as well. So when you're sitting there thinking about the different ways of attacking, you could say, well, is there something along the lines of spoofing that would help, or is there some information disclosure that would help, or whatever the case may be. And you'll do a better job with this, the more you know about the topic itself. So we're going to do this big example of HTTPS. Part of the reason it's going to take 3 lectures is I'm going to explain how HTTPS works. So I'm going to make you domain experts in that protocol, and that's sort of what we need in order to actually do the analysis itself. Okay, so what does an attack tree look like? So an evaluation framework look like a chart. What does an attack tree look like? So it looks like a tree or a graph. So there's kind of like a root of the tree, and there's a bunch of leaves. So think of things like branches that are kind of forking out. The root of the tree is what the adversary is trying to do. The leaves of the tree are going to be the actual attacks themselves. And then the path is sort of like how do you get from the adversary's goal to the leaf? And the reason to put it in a tree is sometimes some attacks are related. Like maybe there's 10 attacks, 2 of them are completely different, but one is just a variation on the other. If it's a variation, that means that in the tree diagram, it's going to share a lot of the same branch, and then maybe at the very end it forks. Whereas some attack that's completely different will go down a completely different path of the tree. Okay, this will make sense in a few slides when I show you what it looks like. And when you have it and it's done and you're looking at it, you can sort of read the chart read the graphic, the tree, by starting at the root node, and then it kind of tells you a story of the attack. Right? Like the adversary wanted to do this, but they couldn't because there was this thing that blocked them. So they tried to get around the thing that blocked them, which they did by doing this. But then there was this other block, and then they got around the block by doing this other thing, and then here's the attack at the other end. Okay, so that's sort of the idea of it. And this is more of a tip. I guess it's not a rule that you have to do, but the best way to do it, I find, is to think about what stops you. So you write down the adversary's goal and you just say, well, why can't the adversary just do it? And it's usually because there's something that stops them. There's some defensive mechanism, okay? So then you make defeating that defense mechanism the next goal. It's the next leaf in the tree, or the next node in the tree, okay? Then you say, well, why can't they just break that defense mechanism, right? And then you'll say, well, this is the reason. And then you'll make breaking that reason the next thing in the tree, okay? So I'll show you an example, and this should hopefully be clear. Okay, so let's do a tree. All right, so the adversary's goal is, I parked at Concordia, and I have to pay to get out, and I don't want to pay. Okay, it's that simple. So that's my goal. My goal is to leave this parking lot. It looks something like this, and I don't want to pay. All right, so to make this a tree, what I'm going to do is, I'll set leaving the parking lot without paying as the goal. So that's going to be the center goal, okay? Then we can think about, like I say, the tip is like, what's stopping me? So let me just ask you, what stops me? Why can't I just leave without paying? Okay, so there's this robotic arm thing that goes, right? And how do I, like if I do everything right, how do I get that arm to move? Okay, so I have some sort of ticket, I put it in. So everyone that puts a ticket in, the arm's going to move? Or do I have to do something to the ticket to get it to move? I had to pay, okay? And so that payment's somehow recorded on the ticket. Now the ticket's going to move the arm, okay? So these are kind of the defense mechanisms, okay? So if I put a random piece of paper in, it's not going to move. If I pay and it's done right, then it's going to move. So you could think maybe I attack the payment or the ticket or something like that, right? If you get a fake payment or a fake ticket, then I can get out. or I can attack the physical infrastructure. So there's the arm, there's also like the construction like bollards and things like that that are sort of stopping me. Maybe I can just drive around or that type of thing, okay? So that's good enough to sort of pencil in the start of the tree. So we can think about, there's the arm and the physical barriers, so we can try and attack them, or there's the payment infrastructure. And there might be more to it than that. This is just a sort of exercise, okay? So let's start with the arm. So how can I get around the arm? Okay, so one thing is, let's say someone else is leaving. Okay, the arm goes up for them, right? Now, I might have a car with a trailer on the behind it, right? So that's going to look like two things going over, and a car following another car is basically the same thing. So the arm's not going to come down. Okay, so there you go. So that's an attack. So then we can put that in the tree. So that's a leaf tailgating, right? And then we need to connect it to how it evades the robotic arm, which we'll leave that detail for a second. Does anyone else have any brilliant ideas? Okay, so you could just drive right through it. You could drive through the wall. You could, do whatever. You could try and drive over the curb if it's outdoors, that type of thing. Yeah.
Yeah. So is it goal to evade without being noticed, or just?
So that's another distinction that you could make. So it's a good question. So like, some attacks will leave a trace, and so then there's like a deterrent effect because you're going to get caught later and then you're going to get punished, and then there's other ones that don't. So that's what you would put into the goal itself. So right now the goal doesn't specify, so that means we're open to both kinds of attacks. But you could modify the goal and say, I want to leave the parking lot without paying and without getting caught, more or less, or something like that. You could refine the goal, and then you would pull back on the attacks. Yeah.
You can fake the ticket.
Okay, so we can attack. So I'm going to put that under evading the payment itself. But yeah, I'll take those types of answers too. So what does fake a ticket mean?
Take another one. You can use an old ticket, someone else's ticket.
Okay. So it could be like the payment itself. So maybe the device that takes the payment. Maybe it's like fake money, literally, like I hand over a counterfeit bill. Or there might be some sort of swapping kind of thing. Okay, so let me ask you a different question. Let's say I go into the parking lot, I drive around, there's no spots, it's full, and I leave within a minute of going into the parking lot. Do I pay? No. Okay, so if I want to leave without paying, why don't I just go up to where the cars come in, get a new ticket, and then just leave with the new ticket? Right? Now, there actually is something that stops you. Does anyone know? You can't do that. Yeah, so there's usually some sort of sensor, like a weight, let's call it a weight sensor, okay? So this is like attack, defense. So I want to leave the goal without parking, I want to leave the garage without paying. I'm going to try and do it by evading payment. I'm going to do it by getting a new ticket. I can't get the new ticket because there's a weight sensor. So how do I attack the weight sensor? If I can attack the weight sensor, then the whole attack works, okay? So how do you attack a weight sensor? Well, I could get a bunch of my friends to stand with me, right? 10 of us all stand there and we look like a car. Then we could maybe get a ticket out. Maybe I have a friend that has a car. They pull up, I get the ticket, they reverse so they don't actually go through it, right? Or maybe they go through and then they give me the ticket once they're through on the way out, and then I go out after them. And so there's all sorts of things, okay? So an attack tree sort of tells the story of how you would sort of do it, okay? Now, let's think about stride too. So faking a ticket, that's a good spoofing attack. Driving through the arm is kind of like a tampering attack. We might tamper with the payment device or like where you put the ticket in or something. Anything that's computerized could technically be tampered with. What about repudiation? Would there be an attack based on repudiation? So repudiation is sort of like, I didn't do this thing that I did. So what if you say I paid?
You can call the operator and say, okay, this is not working.
Yeah, exactly. So you could call and say, hey, I paid, but like I paid my ticket and it's not opening. What are they going to do? Are they going to come over and inspect your payment, or are they just going to press a button and it opens, right? Yeah, so repudiation usually works for low value things. And it works once. What if you park there every day for a month and it's your 30th day in a row saying that it's not working and it's working for everyone else, right? Then they might come over and look at your payment, right? So repudiation is the kind of thing that might work once or twice. Another thing that happened to me accidentally, the one time I left without paying, is I actually folded the ticket when I put it in my pocket, and it had this barcode, and so it was unreadable at that point. So like it had a crease in it. And then they just were like, who cares, just leave, kind of thing. So again, every day I could like crease my ticket and just be like, oh, it's a mistake, sorry. And then they would just let you leave. Now, let's think about that mechanism that they just let you leave, right? So like, is there a button or something somewhere that opens the arm?
Yeah.
Okay, so there's got to be some sort of override. Well, that's another attack vector, right? What if you just walk up and push the button and then drive off, right? So usually there might be a key, right? But can you get a copy of the key, right? If you can get a picture of a key, you can 3D print a key. All you need is a photograph, okay? So security guards walking around and they have the keys like on their belt, like hanging, and it's just sort of dangling there. You can take a picture with your phone. They don't even know it. And you can 3D print the key, and then you can just unlock it and go, okay? So an attack tree, this is sort of a fun example, okay? But it is, like, everything is game. Like, the adversary, like, you might say, oh, that sounds like a stupid attack. But if it works, does it matter? No, the adversary, like, they want to do whatever they can do, okay? They don't care if it sounds stupid or if it's too simple of an attack or anything like that. It's just whatever works, okay? So that's the idea of an attack tree, is that you really think about everything that you can possibly think about, and if as long as it works, we don't care. We don't care if it's silly or easy or anything like that, okay? And it's sort of one place for all of these attacks to sort of hang out together in a single data structure. So this is what it might look like. So I don't know that everything I said is in this tree, but it's just sort of an example. So the goal could be to evade the robotic arm. Then you could physically do it by driving around. You could drive through it. You could tailgate another car. Oh, another one we didn't talk about is, what if the power goes out? Does the arm stay down or does the arm go up? So usually it actually goes up. So it would, it depends exactly how it's rigged, or say there's construction or something like that. Like, there's a lot of times where I've left a garage and the arm is just up for reasons that no one knows, kind of thing, right? So if you could trigger one of those conditions and it just fails, so we call this fails open, okay? So a system that fails open, it basically turns security off in a failure mode. There's other ones that fail closed, and we're going to see fail open later, okay? So we're going to see that this sometimes is a problem in other kind of security systems. So the attendee can override it. So they may have a key. You could 3D print it. You could use some social engineering, like to tell them a story about why you can't pay or you already paid or whatever, and then they'll just override it for you. So these are just some pictures of someone driving through the arm. There's one, the middle one's like the worst security ever. You can just drive around it, and you can see because of the snow, lots of people actually do that. And then this is what like a 3D printed key would look like. And then on the other side of the tree, evading payment, you could use counterfeit money. You could use repudiation. I already paid. The ticket, you could try and tamper with it. You could ruin it so that it's not usable, and then they'll maybe just let you out. You can try and get a fresh ticket that you don't have to pay, because you usually pay by the number of hours that you're there. But the thing that stops you is the weight sensor, so then you can have lots of friends, or you can get a ticket with another car. Another thing you could do is a chain attack. So a chain attack would be, you wait for someone else to come in, and you say, I'll take your ticket from you. Now they're stuck without a ticket, but they do the same thing. So then when someone else when they want to leave, they also wait for someone else to come in. They take their ticket and they leave, and then that person's now stuck without a ticket, right? Maybe you give them the original ticket or whatever, just so that they have something. And so you can basically get a whole bunch of people in a chain to leave for free. The last person's going to end up paying or have to somehow get out of paying or whatever. But you can have an infinite number of people that leave that way before you have to sort of deal with the last person. Okay, so you can think of that as kind of a chain attack. Okay, so this is sort of what the tree looks like. So you can see that sort of attack, defense, attack, defense. So I want to evade payment, I want to get a new ticket, but then the weight sensor is the defense, then I'm going to defeat the weight sensor, and it kind of tells a story, right? I want to leave, I don't want to use the ticket, so I'm going to get a new ticket. There's the weight sensor, it's a problem, so I get a lot of my friends, we stand on it, I get the fresh ticket, and now I can leave, okay? So as you go from route to leaf, it also kind of tells you the story of the attack itself. Okay, questions about attack trees now that you've seen them? Okay, so what we'll do is now we're going to do a longer example. And so the example will be concerning this HTTPS protocol. And basically the adversary's goal is going to be to break that protocol. And it may seem like a technical protocol thing, but there's a lot of interesting ways of attacking it that have nothing to do with like cryptography. Yeah.
That's related to the style of the tree.
Mm-hmm.
Normally are verbs or something like that, or we can just write it like that.
Yeah, like this is fine. So there's no like language. I haven't thought through that. There might be. I linked to like that. The book that came up with Stride also has a chapter on attack trees. So they might have some rules. Some of them have like logic that you embed in the tree. But to me, anything that tells the story is fine. So as long as I'm reading and I know I'm getting what you're saying, I don't care so much about like how you do it type of thing. Yeah.
Do you need to put a difference with attack?
No, not necessarily. So that's just more, put that under the tip category. So when you do them a lot, you realize that that's a good way to kind of start, but it's not a necessity. You don't have to do it that way. Yeah. Okay, so the longer example is going to look at this thing called HTTPS. So HTTPS, I'm sure this might be review for you, but anyways, HTTP without the S is basically the network protocol for like downloading websites. So you go to a website and you say, give me the page, the HTML page, and then it sends it to you. So HTTP is the back and forth, okay? We don't care at all how HTTP itself works. It works somehow. It's magic, okay? But anyways, that's it. The problem with HTTP is there's no security on it. And so what people propose is let's make a secure version of HTTP. We're going to layer some cryptography on top and it's going to help secure it. And so we call that HTTP secure or HTTPS, okay? And the idea is that you'll now have a secure tunnel between the user and the website. And we'll talk about what that means exactly because secure is kind of vague. So anyway, so HTTP is the network side. The cryptography that's used is called SSL or TLS. So some people say HTTP over SSL TLS, which is a fine way of thinking about it. But anyways, the SSL and TLS provide the security. And you can use it with HTTP, but you can also use it with other things. Okay, so technically they're kind of like two standalone solutions that are being glued together in this particular case. Okay, SSL came about in 1995. Netscape came out with it first. 1.0 was just like a private thing, and then 2.0 was the first public release of the technology. Then there was SSL 3.0. Then Netscape was a private company, and people started using it a lot, and they said this is too important to have one company in charge of. And so what we're going to do is we're going to hand it off to there's this organization called the IETF that do a lot of standards around the internet. And they have representatives from different companies, but it's like its own sort of nonprofit, kind of quasi-regulated by the government kind of thing. And so they said, let's let them do it. And so they decided to change the name. If you've ever done like networking, you know the OSI model, there's both transport layer and a session layer. And so SSL stands for secure session layer. TLS stands for transport layer security. And so part of the name is getting reflected, like putting it in the proper place in the OSI stack. But if you don't know what OSI is, it doesn't matter. But the point is that they changed the name. Okay. So then with TLS, it started at 1.0. And then the current version is TLS 1.3. That came out about 5 years ago in 2018. And now there's always talk about the next version and what are we going to do next and that kind of thing. Okay, so sometimes I'll say SSL, sometimes I'll say TLS, depending how lazy I am, and I mean the same thing. They're the same thing. Okay, what does it look like? So you go to a website and this protocol is being used. How do you know it's going over HTTPS as opposed to just HTTP? And so the answer is there's two indications that you get. One indication is that there'll be a lock that appears beside in the URL bar. So in Safari, this is what it looks like. And the other thing is if you're manually typing in a URL, or if you care to look at the actual URL itself, you'll notice that it's HTTPS:// and then the URL, okay? So those are the two indicators. They more or less mean the same thing. HTTPS technically means you tried to do HTTPS, but if it fails, it might still display HTTPS there, but it won't show the lock. So the lock is technically means that it succeeded. So like this, you tried, your intention was to use HTTPS and now you are using HTTPS. That's what the lock means. You can type in HTTPS and it might fail, but then it just won't show the lock itself. Okay, so the lock is the more like kind of universal indicator of the fact that not just that you're trying to do it, but that it's actually working. Okay, so how do you end up on an HTTPS website in the first place as opposed to an HTTP? So there's a couple names or a couple ways of doing it. So the first is because you explicitly typed it in. So I wanted to go to Concordia. I wanted to be over HTTPS. So I typed https://concordia.ca. Okay. Then my browser will try. It will say, hey, I want to talk SSL with you. And then the website either will say, I don't know what you're talking about, or I know what that is, and then we'll end up either with the lock or without. Okay. But usually we're not typing URLs in, right? Sometimes if you know the URL, you might type it in. And a lot of times you're not actually typing https://, right? You'll just put in CON and then your browser will be like concordia.ca and you'll press enter, okay? So there's other ways that you end up on the website. So one is that you're on another website, it links to it, okay? So you click on it and you end up on HTTPS, okay? Now in that case, who decided to send you to the HTTPS version of the website? Why did you go to the HTTPS as opposed to the HTTP?
Because the website is certified by SSL, certified, so first it will invoke that certificate.
Okay, that's too deep. It's simpler than that. That's coming up though. Yeah. Too complicated. Not complicated enough. Okay, the answer is just it's encoded that way. So like if I have a website, I write the HTML, and when I put the link into it, I choose. So I can put HTTP, then everyone that clicks on it will go to HTTP, or I can put HTTPS. Okay, and then everyone will go to HTTPS. So the site that sent you to the site, they chose whether to send you one way or the other. Okay, just in the HTML itself. And keep that in mind because this will become relevant later. Another thing is if you basically can't go to Google not over SSL. Because Google is world famous, every browser knows about it, every browser knows that it's got to go over SSL. And so even if you type it in, or if you just type search terms into Safari and hit enter, it automatically redirects to Google, and Safari just knows it, okay? So technically we call this preloading. So Google, the company, went to Safari, the browser manufacturer, and said, we only use SSL. And then Safari said, fine, we'll never try to not use SSL. Or they might go a step further and say, we only use this key or this certificate, and you don't know what keys or certificates are yet. But anyways, they can lock down things even further, okay? Now, another thing you can do is if you're just like my website, right? I'm not Google, like I don't know anyone at Safari, so I can't get it preloaded into Safari. But what I could do is I can advertise the fact that I only use SSL on my website itself. Google also is a search engine. They have these like, web trackers and things like that. They'll pick it up. And then in Chrome, because they also make a browser, they'll say, oh, we when our bots were calling the net, indexing things for the search engine, they noticed that you only use SSL. We're going to put that in Chrome so that every new Chrome user knows that, okay? Now, if you blow it, let's say you get it wrong, and you say you only use SSL, but you don't actually, then the browser is not going to let the users go to your website. And so like you can mess up. A lot of people don't want to touch this stuff because if you get it wrong and you pin the wrong thing, you can't undo it, and it's cryptography. It's hard to undo. Like if you say the wrong key or something like that. So anyways, but the pinning only works if the person's either already gone there. Someone's had to have gone there before. So it could be the user, they go the first time, they notice that you're setting that you only use SSL, then for all future times, they'll only go to you over SSL. Or Google went there first, but someone went there first, okay? So we call that threat model trust on first use. And then the final thing is you might actually just go to the HTTP website. So you go to Google without HTTPS, and then Google says, oh, we use SSL, so they'll redirect you, okay? Then you'll redirect, and then you'll ask for the HTTPS, and then you'll end up on the HTTPS, okay? Now, this is a dangerous way of doing it, because if there's an adversary in the middle, they can stop that redirect from happening, okay? They can just drop that redirect, okay? So this is like the least ideal way that you want to do it when there's an adversary, but we'll circle back to attacks later. Okay, so the idea of HTTPS is I'm not going to go into crypto details. You take 6110 and learn the crypto details, but just think of it as a secure tunnel, okay? So you have this tunnel. Alice is at one end of the tunnel. The website is at the other end of the tunnel. And if it works correctly, we don't care if there's an adversary in the middle. Let them be in the middle. Let them look at all the traffic that's going back and forth. It's all encrypted anyways. Who cares? Okay? So that's the ideal. So the ideal circumstance is when this protocol works, we don't have to worry about where the adversary is because they can't do anything anyways because it's a tunnel. Okay? So what does that mean to be a tunnel? What does that invoke for you? Like what's the security property here? What will we write down as the security property? In Stride, is it a spoofing thing, a tampering thing, an information disclosure thing? Like what is the tunnel? So some people say spoofing, some people said tampering. What does the tunnel stop? What does it stop the adversary from doing? Okay. All right, so the basic property in Stride, we would put it under information disclosure. Okay, so we want to keep things confidential is the flip. And so that's what the tunnel does. So it basically stops the adversary from reading any of the data that's on the path. Okay, so that's message confidentiality. Now, SSL actually does more than that. So this is what most people think of. Sometimes people just think of it as just doing this and nothing more, but it does more than this. So is there any other ideas about what it could do for you? So someone said tampering. What would that look like? Okay. Okay, so let's say we change the data just more vaguely as it goes across. Okay, could we do something about that? So you can't stop the adversary from changing it, but you can make it detectable so that if it is changed, you know that it was modified. So SSL does that as well. So we call that message integrity. So any modifications to the data that's made are detectable, and then you can just ask for it to get resent. Or if the adversary is always messing with it, then you just give up. You can decide what to do, okay? So it's not just confidentiality, it's also integrity. Sometimes you actually don't care about confidentiality. Say you're downloading an app from a website, you want to install it, you actually care about integrity, right? You don't want the adversary sticking malware in the app as you're downloading it, right? But it's not a secret, it's a public app, anyone in the world can download it, there's no secrets involved. So in that case, you don't even care about confidentiality, you only care about integrity, but you would want to do that over HTTPS because you want the integrity. If you did over HTTP, then there's the threat that it gets modified, right? Then you can like get a hash of it and compare it, but then the adversary could modify the website that's showing you the hash, blah, blah, blah. So anyways, you want SSL. Is there anything else that it would do for you?
Non-reputation.
Okay, so it doesn't do anything with non-repudiation. It's a nice idea, but yeah. Okay, so authentication means?
You know who you're speaking with, like the server.
Okay.
Point.
Exactly, yeah. Okay, so server authentication is the third and final property of it. And so this one seems simple, but it's actually probably the most important. because from the user's perspective, they're dropping messages into a tunnel. But where does the tunnel end? If the tunnel ends at the adversary, right, then who cares if it provides confidentiality and integrity, right? So if you don't know where that tunnel ends, then you might as well not use the tunnel at all. Okay, it's that bad. Okay, so knowing where the tunnel end is like the most basic property that you need before you can even think about confidentiality and integrity. Okay, so when we attack this protocol, a lot of the attacks are going to be about, can we get the tunnel pointed at us instead of the website? That would be one way of breaking this protocol. Not the only way, but it would be one where we don't have to break into the tunnel or do anything with the tunnel itself. We just get the tunnel pointed at us, and then it doesn't matter. The tunnel can be bulletproof. We're still attacking the system. Okay, so just as illustrating that if the tunnel ends at the adversary, they can always then create a tunnel to the website. So if the website sees that messages are coming out of a tunnel, the user sees that messages are going into a tunnel, right? So everyone's happy. Everyone thinks, oh, we have this tunnel between us, but really the adversary's in the middle. They're taking stuff out of one tunnel, reading it, modifying it, and then they're putting it in the other tunnel, and then they're sending it off. Okay, so an adversary like this we call man in the middle, which is sexist, but it's just the term that was used. You can think of it as person in the middle or malware in the middle, but I'll use the acronym MITM, man in the middle, and that's the kind of attack. So I mean, like someone that's in the middle of the communication, they're seeing everything, and they might be relaying. Sometimes we'll distinguish between what we call a passive adversary who's listening but not modifying, and an active adversary who's actually changing things. But in general, we'll just consider active adversaries. So we'll always assume that they're able to modify it as well as listen to whatever there is to read. Okay, so the idea of the next couple of classes is to build a monster attack tree. And the attack tree will have the node of the attack tree, the starting point, the root of the tree, will be to observe traffic that's being sent over HTTPS, given that we're a man in the middle. Okay, so the adversary's already in that position. We don't care how they got in the position. Okay, it could be that they're the ISP and they're corrupt. It could be that the government is spying on you and they have servers in the back end. It could be that the Wi-Fi router that you're sending your traffic through is corrupt. Someone puts up a fake Concordia University. Your computer's like, oh, I know that network and connects to it, but it's really like a rogue Wi-Fi thing. It could be malware on your computer. It might be, the tunnel might be ending before it even leaves your computer. We don't care, okay? But the adversary is somewhere in the middle. They manage to get themselves in the middle. We can't assume an adversary cannot do that. Okay, it's very reasonable that an adversary can do that, and this protocol is meant to protect us from that kind of adversary. Okay, so it's a reasonable assumption that this should not be possible. Okay, and yet we're going to come up with 50 different ways that this is possible by looking at different aspects of it. Okay, so at a high level, we're going to cluster our attacks around three basic approaches. Okay. So the first approach is actually the easiest from the adversary's perspective. We're going to assume that SSL works perfectly, okay? But they're still in the middle and they're still able to see stuff. It might be jumbled up, it might be encrypted. They might, if they flip bits, it might get detected. But they're still there, they're still seeing something, okay? So is there anything that they can do just even if the protocol is working fine and they're just looking at it? Okay, so that's the first question. Okay, so we'll think about what could you see anyways. Okay, then we'll think about basically how do you break into the tunnel. Okay, and this we'll treat at a pretty high level because it goes into a lot of crypto details if you want to understand all the methods. But I'll give you the high level intuition for how you might break into the tunnel. And then the third thing will be get the tunnel pointed at us. Okay, if we can get the tunnel pointed at us, then the tunnel can work fine. We don't care about it. We don't have to break the tunnel. We just have to get it pointed at us. Okay? So we'll do each of these. We'll do a bunch of attacks of type 1. We'll do a bunch of attacks of type 2. And we'll look at a bunch of attacks of type 3. Okay, so we'll start with what can you learn if you're just looking basically from the outside of the tunnel. Okay, so the sub goal from the tree, it's kind of small, but it says recover, I put partial in brackets, or it's not in brackets, but the idea is that with these techniques, we might not be able to recover everything that goes over the channel, but we could learn something that's more than nothing. And we're going to do it through external observation, meaning we're not breaking into the tunnel. We're just sitting outside the tunnel and watching what goes by. Okay, so to do this, we're going to assume HTTPS works fine. There's no flaw that we're going to exploit. And we're just asking, does it actually do what it promises to do? Does it offer all of these properties against a man-in-the-middle adversary, or can the adversary still learn things? Okay, so let's say that Alice wants to go to concordia.ca. Okay, so Alice types whatever. We'll say she clicks on a link or she types it. We'll say she types it. So she just typed concordia.ca in her browser bar. She hit the enter key. Okay, what happens? How does she end up talking to concordia.ca?
DNS.
Okay, so what's DNS?
Resolving the name to the IP address.
Okay, why do we need DNS?
You can't remember all the IP addresses.
Okay, so you can't remember all the IP addresses. Why do we need an IP address? Why do we need to connect to a server with an IP address? Okay. So the point is that if I tell my browser, go to concordia.ca, there's a million servers out there, and it doesn't know how to navigate to that server. Okay. So what it needs to do is it needs to have kind of like a hierarchical sort of routing system. So first, think about a telephone. So like if I call you, you have a number. First off, you have an area code. So that sort of routes my call to that general area. And then you have a specific number, and it belongs to Bell. So then it will go over to Bell, and then Bell will say, oh, that belongs to this SIM number, right? And then it will go on the cell network and find my SIM and then route the call, kind of thing, okay? So the internet's kind of the same way, okay? So you can't just drop a packet and say, go to concordia.ca. The routers don't know where to send it, okay? So what you do is you put it in numbers, and the first number, it sends it to that general area, all the things that have that first number, and then it maps it to the second number, and it gets more fine-grained, and eventually it ends up where it's going, okay? So that's very high level, okay? Now, as was said, you don't remember the IP address, right? That's too much. Just like phone numbers, you might not remember it, okay? So it's easier to remember a name, but now you need like a telephone book, okay? So I remember concordia.ca, I don't remember the IP address. But the my computer needs the IP address, so I need to look it up in the phone book, okay? So that's what DNS is. It's basically the phone book for URLs being converted, or domain names being converted into IP addresses. DNS is its own thing. Like there's multiple servers and things that are involved, and we're not going to touch on a lot of the details, right? For now, we're just going to assume it's just a computer you ask and it tells you the response. That's not actually how it works. It's actually a big distributed system, but we don't care about that for now. Later, we'll maybe dig into the details a little bit later. But so you go to DNS and say, hey, I want to go to concordia.ca, and DNS says, great, I have the IP address. This is where you want to go. So now you have 132.205.244.70, and so your computer says, okay, I'm going to like 132 dot something, and then it sort of knows you go right or you go left, and then it ends up there, and eventually it finds its way to the right server. Okay, what if an adversary is sitting in a man-in-the-middle position between you and DNS? What do they learn? Is it encrypted? Do they learn nothing? Do they know that you're going to concordia.ca because it's not encrypted?
Yes.
Could they change the IP address to something else and send you somewhere different?
Yes.
Okay, so definitely they can read. In all versions of DNS, they know what you're doing. So they already know, they don't know what you're doing on concordia.ca yet, but they know that your intention is at least to visit concordia.ca. Okay? Can they modify it? It depends. So there's two kinds of DNS. There's basic DNS, where they could modify it. And then there's DNSSEC, which is the secure version, that is not widely deployed for a whole bunch of reasons that we won't go into. If you use DNSSEC, there will be a signature on the DNS record, and then an adversary couldn't modify it, or it would be detectable if you could modify it, okay? So you might have integrity at best, but you don't have confidentiality for sure. Now there is a suggestion to run DNS over HTTPS, And that's another thing that's also not in wide deployment, but people play around with it. But for now, we're just going to assume DNS is just vanilla DNS, so no integrity, no confidentiality. Okay, so DNS queries are not encrypted, so the adversary learns the domain that's being visited. Okay, then what happens is you now have the IP address. You're going to do this thing called a handshake. Doesn't really matter, but basically you're going to say, hey, I want to set up a secure tunnel. The server will say, okay, I know what you're talking about. And then you'll go back and forth, and eventually a tunnel will emerge. Okay, those details, maybe in a couple slides, we'll go into a little more detail, but you don't have to know much more than that. Okay, but let's assume that the tunnel's already in place. So the handshake has happened, and the tunnel's in place. And the adversary is now watching your traffic go back and forth, but it's encrypted. Okay. Do they know the domain that's being visited? Do they know that you're connected to concordia.ca? Or is it just like, this is encrypted traffic, I don't know where it's coming from or where it's going?
They know.
Okay, why do you think they know?
The IP headers are not encrypted, just data payload.
Okay. So the encryption is going to cover some stuff, think of it as an envelope. Some of the stuff's going to be in the envelope, and some of the stuff's going to be on the outside of the envelope. Why would the IP address be on the outside of the envelope? Why don't you put it in the inside?
The request basically, if it's encrypted, you cannot route it. Right?
Exactly. So the envelope wouldn't know where to go if you didn't have the IP address on it. Okay? So like there's no way around that. If you want the packet to go to the right server, you have to tell the network where it's going, right? So you just cannot put that inside the envelope. Okay? Basically everything else that you can think of is in the envelope. Okay? But that routing information is not in the envelope. Okay? So what that means is that the adversary can also tell what domain you're visiting by looking at HTTPS traffic. Okay? So it's not going to hide what domain. They'll get the IP address, then you can go to DNS and do a reverse lookup. And then you can say, this is the IP address, what's the domain that matches it. Okay? So the main thing to keep in mind is that just the domain name itself could be privacy invasive. If an adversary knows that you're going to a particular website, they can conclude all sorts of things, okay? There's all sorts of sensitive websites that you might visit where knowing the domain of it is enough, okay? So I don't care exactly what you're doing on that website, but I just know, like just the fact that you're going to that website at all tells me what I want to do in response. Like say it's a corporate environment, right? I can tell, different things. Like it could be a medical condition, it could be adult content, it could be some sort of politically sensitive topic in different countries. Different countries will have these firewalls set up. And so all of that stuff could just be in the domain itself. And you might get action taken against you just for visiting the domain, period. Okay? Regardless of like what you're actually doing. Okay? So HTTPS does not protect you, doesn't protect a man in the middle from discovering what domain that you're going to. Okay? So already it's not that great of a protocol. It's maybe doing less than you think. Okay, now consider this. This is a website. So this is Wikipedia. This is the local soccer team, CF Montreal, and this is their website, or their article on Wikipedia. Okay, so this article, I went to this website, I read this article, and it came to me over HTTPS. How do I know that? Okay, because there's a lock. Wikipedia, by the way, used to not use HTTPS. Then there was a period of time where they had HTTPS enabled. So if you explicitly typed in HTTPS, you could go to it. But by default, Google and other search engines would send you to the HTTP version. And then eventually they switched because of this. Actually, the Edward Snowden thing, I showed you like a little clip from the documentary, the guy with the who put the blanket over his head when he typed his password in. That guy leaked a bunch of information about how the NSA works. It freaked everyone out, and then everyone turned on HTTPS by default, including Wikipedia. But anyway, so now all of Wikipedia comes over HTTPS. And so, okay, so what happens in this case is just the same story. I go to DNS, I get the IP address, and then now I'm not showing the tunnel anymore, but if there's a little lock icon, it just means that it's going over the tunnel. So what I'll do is I'll say, okay, I want this article. This article is at the location wiki/cf_Montreal, and it's an HTML document. I want to get that. And then the server is going to send me that actual HTML document itself. Okay. Now, we know that the fact that I'm going to Wikipedia or to that IP address, that is not inside the envelope. Okay, so that's on the outside of the envelope. What about the fact of what file I'm asking for? So the fact that I'm asking for this article that's at wiki/CF Montreal, that's called the path, right? So it's on the path of the domain. So the domain itself is not encrypted, but then the path itself, is that encrypted or not? What do you think? You don't have to know the answer, just give me a guess. Okay, so not encrypted. Why would it not be encrypted?
So, now that I think about it, might be.
Okay, so let's say it was encrypted. Is there anything that would go wrong? Encrypted because
Because it will lead us to the root.
yeah.
If we expose it, it will lead us to the root. Like, what is the source code?
That's true. That's all true. But are we safe to put it encrypted? So we want to encrypt it, but are we safe to do it? So the main reason why you can't encrypt things is because you need them to like make sure that things go to the right place. Okay. So who needs to know this path? Do the routers that are on the back end, routing my packets, do they need to know the path?
No, just
Just the server, right? So the server needs to know it because they need to know what website to send back. They're the ones that are at the other end of the tunnel, so they're going to decrypt it anyway. Okay, so this is safe to put in the envelope because it's the server will decrypt it and then read it. Okay, no one in the middle needs to know it. Okay, what about the response that comes back, that HTML document? The name of the HTML document, the actual contents of it, is that encrypted or not encrypted? Encrypted. Okay, so same reason. It's for me. It's for my eyes only. To get the packet to me, to get the encrypted payload to me, you don't need to know that information. Okay, so all of that stuff is sort of inside the envelope. Then what will happen is when I read that index.html file, it will say, oh, there's a bunch of images, like the logo of the CF Montreal and the little flags beside all the players' names. You have to go and get all those images. Okay, so now I'm going to go get those images. Now, first thing, do I go over HTTPS to get the images? I mean, I got the index.html file. That came over SSL to me. What about the images itself?
Over HTTPS.
Yeah, does it go over HTTPS? As opposed to HTTP? Or how would I decide? Okay, so it would be from the link in the index.html. Okay, so the HTML, when they say, go get this image, they have to give the full URL of it. So if they tell me, go get the image over HTTP, my browser will do that. Okay? If they say, go get it over HTTPS, my browser will go over HTTPS. Okay? With some constraints that we'll see in a second. Okay? Again, this is being hidden. So the actual request for that file is being hidden. That's inside the envelope. The actual image that comes back, that's hidden. The fact that it's an image as opposed to something else is hidden. All the adversary sees is that now I'm going to this other domain, upload.wikipedia, and I'm downloading something from it. Okay? So that's the sort of what they see. Okay, so we're going to assume the adversary is sort of on all these connections so they can kind of see everything that's going back and forth. And if you go into, actually I can demo this. So all of you can do this from basically every browser has the same thing. You might have to turn on developer mode to get it. But this is called inspect element. And if I go to the network and I have caches disabled, so I'm just going to do a refresh on this website. So you can see that this is all the stuff. You can't really see it. It might be better on the slide itself. But and this seems to be sorted wrong. There we go. Okay. Now it's sorted by the order that I got things in. Okay. So first I went to Wikipedia. I got the actual HTML document. The HTML document then said, go load all this other stuff. Okay. So I got like a CSS file. It's kind of like the layout of the website. I got some JavaScript. So that's going to run some things. another style sheet. Then I started getting a bunch of images. So all the images came in. I got some JavaScript at the end again, and I got some images and things like that. Okay, so that's sort of what most modern websites look like. They weave a whole bunch of content. It's all coming from different servers. It's getting dumped into the same website that's being displayed to the user. Okay, so from an HTTPS perspective, we have to think about what's being hidden and what's not being hidden, and then we also have to think about what are the ramifications if some of this is loaded over HTML or HTTPS and some of it's loaded not over it. What do we do in that case? Do we like that scenario or not? Do we show the lock? Like if one of the images came down without encryption, would we show the lock or not? So these are the kind of decisions that we have to make. Okay, so we've already sort of gone over this already, but just again, so we have this, that says Adidas short on black. We have this file name. So that file itself, is that encrypted or not? So this image file we got, that is encrypted, okay? The fact that we got it from upload.wikimedia.org, was that encrypted information or not encrypted information? Not encrypted, remember? So the otherwise the packet wouldn't have got there. Our request would never have got there, okay? The fact that it's a PNG file, which is an image, as opposed to an HTML file, as opposed to JavaScript, could the adversary tell what it is based on just looking from the outside of the tunnel? No. Okay, so it's just going to be a payload, and that's it. Okay. Every resource has a size, so like some images are bigger than others. Could the adversary tell the size of what's being downloaded?
Not of the file, but the encrypted version.
Okay, so is the encrypted version of the file, does that hide how big the file is? I'm smiling a little because I want you to think about this. So it sounds like a very casual question. Oh, does the length of the file, is that encrypted or not? But what do you think?
Depends. I mean, it's basically split into frames.
Okay.
So you cannot tell it to be
Okay, so there could be some bunching of data, but is it more or less? So I'm going to encrypt it. It's true, I am going to encrypt the file. Okay. So the question really is, does the ciphertext come out to be either roughly approximately the same size? Is it completely different size? Like does encryption also like mess with the file size of things? It's trying to hide it? Or does it come out at exactly the right size? Like what level of granularity? So you would have to know what encryption is. So if you're sitting here not knowing the answer, I don't expect you to know, but I'm just raising the question. So in general, does encryption try to hide the size of things?
No.
It does not, okay? So the size of the ciphertext, which is the encrypted data, will more or less be the same size as the plain text that you started with. Depending on how you encrypt it, there's things called stream ciphers, which used to be used more in TLS. They're not so much, but they're still an option. They'll encrypt it down to the same, the file size will be down to the same byte. So if something's a certain size in bytes, the ciphertext will be the same. And then you have these things called block ciphers. What they do is they take a block of data and encrypt the entire block. And so in that case, the ciphertext, you'll round up to the nearest block size. A block size might be like 256 bits. Okay, so it will round up to the nearest 256 bits. But if you're talking about things that are 10 KB, right, then that rounding error doesn't make much difference. I mean, the ciphertext is going to be more or less the same size. Okay, so it's an important thing to remember is that encryption is length preserving. So it preserves the length of the underlying information. You might say, well, what if we compress first? Okay, so that's something you can do, and that's going to be actually going to create problems. That's going to create more problems than it solves, and we'll see that in a couple slides, what happens if you compress first. But in general, we don't compress. Plus, the data could be not compressible anyway. Like if it's a JPEG, it's already compressed. So compressing it at the network level is not going to do much on top of it. Is that dangerous to know the size of things? I mean, you still don't know what it is. You don't even know it's an image. You see a bunch of blobs and they have a certain size, right? That doesn't, I mean, it leaks a little bit of information, but You can't really do much as an adversary, right? Could you achieve the goal? Remember, the goal is to recover partial traffic from a man-in-the-middle position when it's sent over HTTPS. Could we use the CIISE to do that?
You know the type of media.
Okay, so think about it. Okay, so these are protected, and these are the two things that you can see. So just to summarize, the adversary that's sitting there, it's going over HTTPS. They know the domain that's being visited. Okay, they know that, hey, so they know I'm at Wikipedia. Okay, what don't they know? They don't know what article I'm looking at. Okay, but they can see that my browser asks for 87 resources. Resources meaning images, JavaScript, CSS. Doesn't know what they are, but it knows that I asked for exactly 87. Does every Wikipedia article have exactly 87 resources? Some will have more, some will have less, right? It also sees the size of all of them. Does every Wikipedia article, is the first thing you ask for is some blob that's 3K, and then it's followed by something that's 2.78K, and then it's followed by something 1.13K? Is every Wikipedia article have that? No. It doesn't. This is probably the only Wikipedia article that asks for that exact number of resources, and when you look at the size, because encryption is length preserving, that have those resources of that size. Okay? And so you also know more or less the order that I asked them, because I'm going through the HTML document and it's like, get this image. I stop reading, I just go ask for the image, and then I come back and I keep reading through the document. Okay, so basically everyone that's looking at this CF Montreal page, they're kind of asking for the same number of resources of the same size in the same order. There's a bunch of noise, right? There's race conditions, so things get slightly out of order. There's caches, so I might already have Wikipedia's logo, so I don't have to go and ask it on the network. Okay, so it's not completely deterministic, but there's definitely enough structure there that you could guess which article I'm actually looking at. Okay. In other words, what we could do is we could fingerprint what every Wikipedia article looks like in terms of how many resources it's loading and the sizes of them. And then we can, when we're sitting there looking at people visiting it, then we can just try and match it. We do a pattern match with our sort of dictionary of what all the websites look like, and we can guess with some level of accuracy. It won't be 100%, but it could be close. So the traffic pattern is probably unique. And so this was one academic paper. There's a whole bunch, and everyone's trying to improve the result. But this was like one of the first ones that looked at it. And so they found that you could use this to identify 90%, with 90% accuracy, what actual page someone was looking at. So you already know the domain because it's not encrypted. You want to figure out which page it is that they're looking at. And they tried it on a bunch of websites like healthcare websites, banks, legal services, videos, and that type of thing. Okay, so HTTPS actually isn't that great, right? It doesn't protect the domain name. It doesn't even really protect like which website you're on. You would think that would be a basic thing that would be covered, okay? Now, the good news is that this fingerprinting attack only works if the adversary can first go to the website, build what the fingerprint looks like, and then after they're trying to match it. Okay, so that means the website is something that they can go to and you can go to. Okay, so my Gmail inbox, right? The adversary can't go there first and build a fingerprint for it. It's not a public website. Okay, so this attack isn't going to work on my Gmail inbox. Okay, but if I go to Wikipedia, the adversary can also go to Wikipedia. They can see the same article that I see. So if the adversary can see the same thing that I'm seeing, then they could do this attack. Okay, so this attack is pretty damaging, but it is only limited to public websites that everyone can visit. It doesn't work on like personalized content or content that's specific to you. Okay, questions about that?
Is a subscription also a public website?
So it depends on the content that's being served. So any content that's specific to you is not public, but like say you go to Netflix, you do have to log in, but the adversary could have a Netflix account. They're going to see more or less the same thing. So they could probably fingerprint it. Yeah. Okay, good. All right, so let's go take a 10-minute break and then come back and we'll keep going. All right. Okay, so fingerprinting is this attack. It's one attack. So continuing on with this idea of inspecting from outside of the tunnel, is there other things we can do? So here's a question that I raised earlier, but we didn't really fully answer. What happens if we know now that websites load a bunch of resources from other websites? Okay, so what happens if they load some of those resources over HTTP? So let's say I go to the Wikipedia article and all the images come down over HTTP, but the rest of the website and the root page comes over HTTPS. Okay, you're the browser. You're deciding, do I show a lock to the user because some of the content came down? Do I show no lock? What do I do? So what do you think? What's a guess? Or does anyone know the answer?
Depends on the server, force policies and stuff.
Okay, so there is some stuff that can be set in terms of policies by the website itself. Different browsers also have policies. There might be differences between browsers, but now there's pretty uniform, I think, consistency across all browsers in terms of how this is handled. Okay, so the first thing we're going to do is we're going to distinguish between the kind of content it is. Okay, so we're going to distinguish between passive content and active content. So passive content is content that I just look at, okay, as opposed to execute. So an image, I look at the image. Movie, I look at the movie. Audio file, I look at the audio file. Okay. There is always some danger that maybe like the image is corrupt and my reader of the image, it will trigger something in it. But it's a pretty remote risk. Okay. By contrast, I could download something that actually runs, like JavaScript. Okay. If I download JavaScript and JavaScript is bad, what does that mean for me visiting that website? What can the JavaScript do? It can basically do anything to that website that it wants to. Okay, it can't like jump out of that website to another website or jump into out of my browser to my operating system, unless if there's some, exploit that no one knows about. But in terms of the website that I'm on, if I get just one bad script running on it, that script has control over the entire page. It can rewrite all the resources, it could load new images, it could change text. Whatever I type into that website, it could make a record of, it could phone home with it. Getting bad JavaScript on a website is bad, okay? Basically, it's just, yeah. So that's considered active content. Now, if I load a website over HTTPS and I pull down JavaScript over HTTP and an adversary is in the middle, can they change the JavaScript? They can, right? So they can change it to whatever they want. They can put their malicious JavaScript in instead. Now I download the malicious JavaScript, my browser starts running it, and now it can take control of the website. Even though the rest of the website came to me over HTTPS, right? It can sort of take over the website essentially, or like it's not taking over the website like at the server of the website, it's taking over my view of the website in my browser. Okay, so that's very dangerous. Okay, so downloading JavaScript that's not over HTTPS is dangerous. Downloading an image, the adversary could change it. Okay, so now it's a picture of something else, but it can't do much more than that. Okay, it can't break out of the image and change the rest of the website or things like that. Okay, so most browsers are like, if you download an image, there's a risk there, but it's small, it's acceptable. If you download something like JavaScript, that's really dangerous. We don't want that to happen. Okay, we're not going to show you a lock in that case, and we'll see exactly what they do. Then there's some stuff that's kind of in between. Okay, so there's things like, for example, those CSS files. If you download a style file, right? Is that like JavaScript, or is it like an image? Is it just markup, or is it actually capable of running? And so now, because that standard has evolved, it's considered active content. So it's considered to be as powerful. It's obviously not as powerful as JavaScript, but it's considered to be able to execute in addition to just displaying things. Okay. Another thing is when you have JavaScript, JavaScript itself can open up connections to websites and ask for stuff. Okay. The way it looks is it doesn't use standard HTTP, like GET requests, the way that HTTP normally would. So it uses this XML HTTP request instead. That's something that will come back. But when you see that kind of thing, you know it came from JavaScript as opposed to from the browser, from the HTML page that's in the browser itself. Okay, so different browsers do it different ways. This is how Firefox does it. What they say is you'll see the padlock if everything on that website came over HTTPS. Then we'll show you the padlock. If you see a padlock with an X through it, then what you'll see is that it's mixed content, including active content that came over, not over SSL. And so it's not secure. Also, if you just go to a website and there's no SSL, it shows you the lock. Now, this is a new thing. They show you the lock on every website, but they put a cross through it if it's not secure. So that basically means it's not secure. And then they have like a middle ground. So different browsers have experimented with this over the years, and it's kind of evolved. Do we want to show a mixed content kind of icon where the lock is kind of half on and half not? Because some of the content came down and some of it didn't. So what Firefox does is in the bottom they have a lock with a kind of exclamation mark and a triangle that's over it. Okay, and so what that means is it's passive content like images is coming down over HTTP, it's not secure. Okay, and what all browsers do now is if you try and load, say, JavaScript over HTTP, it will just block it. Okay, so it doesn't display a funny lock. It doesn't download it anyway and tell you, oh, it's mixed content. It just straight out blocks it. Okay, so any active content that comes down over HTTP is blocked. The browser won't look at it. It will see that the request is going out. It won't even send the request. It might break the website because the website might need that JavaScript to run. Too bad. Okay. So the website's not going to work on your browser because your browser decided to just not download it. So it just completely blocks it. Okay. So basically you have 4 levels. If it tries to download active content, it will block it. But then it will probably also not display the lock. I don't know what happens if it, actually we could experiment. If it ends up blocking it and then everything that it didn't block did come over HTTPS, then I think it would still display the lock because it took care of the problematic bit. But anyways, there are some cases where it won't display the lock, and then you could have this mixed content. So if you want to play around with this yourself, there's a really nice website called badssl.com. And it has like basically every possible error that you might want. And so including mixed content here. So if I click on this is mixed content. So like some of the images and stuff came down not over SSL. Another thing I noticed playing around with it, yeah, okay, never mind. So you can see that this image.jpg, there's no lock beside it, so it came down just over HTTP. Safari is not showing me the lock, okay? It is showing me that I asked for this over HTTPS, so the HTTPS is there, but it is not showing me the lock itself, okay? And if I try and download, say, a script over it, then I get this website. And in this case, if I go to the console, you can see there's some error messages. And so it said, it basically tells me what it did. It said, okay, you tried to download this image over HTTP, so insecure content. We did allow it to display it. I see now that you basically can't read that, but I'll try and read it out. It's in a slide anyways. And then in terms of the script itself, it basically says we didn't allow that script to run. Okay, so we completely blocked it. So I think I have this in the next slide anyways. Okay, so the image was okay, but they decided to not display the lock as a result. The script was bad, so it was completely blocked. So you see blocked here. And then there's also the idea of like if I type information and press a button, it sends that information back to the website. And so in this case, it was programmed to send that over HTTP instead of HTTPS. And so this is also warning me that that's there. Now, of course, the user doesn't see this, right? Like this, I open this up because I'm in developer mode in my browser. I'm not looking at this console on every website I visit, right? So that's why, like, do we show the lock or do we not show the lock? That's what the user, the non-technical user, is going to see. I'm just showing you what's happening under the hood. And then let's say I type something into this and hit submit. Then you maybe have seen this before but not really known what it meant. So this warning, the browser says you're about to send this. It's not going over an encrypted channel. Any man in the middle is going to see what you type into this. Do you want to send it anyways? And so then you can decide whether to send it or not. So if you put your credit card number in and you see that message after you hit enter, then an adversary would be able to read that credit card number out if they were in the middle looking at your content. Okay, and so you can see the lock is not displayed in this case as well. So JavaScript was blocked because it's active content. Passive content was allowed, but we dropped the lock icon. And then we have additional warnings around other kinds of things. So that's more or less a summary of what happens with mixed content in Safari. So I switched to Safari. The previous slide was Firefox. And then Chrome will do it slightly different, and Edge or whatever they call it on Microsoft might be a little different still, but most browsers work more or less the same thing. Okay, a final thing you can do is, let's say you're an adversary, you're in a man-in-the-middle position, and you can't break into the tunnel. One thing you can do is you can always just store what you see. Okay, you could build a big data center in Utah, and you could just put like a server up on the backbone of the internet, right? And every packet that goes across that, you store. You just write it down. Now, in 20 years, 30 years, maybe you can break that traffic. Okay, maybe there's some crypto attack or something like that. Now you can break in. Now you can read it. Is there content that might be relevant even though it's 30 years old? Probably, right? You can think like the stuff that me and you are doing, like what we're buying and stuff, like the emails we're sending, probably no one cares about that in 30 years, okay? But if we're talking about like heads of national states and it's military plans or patents or discussions of things, that could still very much be relevant in 30 years, okay? 30 years could go by and people might still care about that. So this is the kind of attack that you might expect from a national government kind of agency. So this is a picture of a headquarters that was built by the NSA. So that's the spy agency in the United States. And no one knows, because it's classified, what it's being used for. But based on like the blueprints and things like that, you can tell it's being used to store lots and lots of data. Okay, what they're using it for, we don't know, but the speculation is that they're just storing all encrypted data that they see in hopes that one day they'll be able to break it. And that's what the NSA's specialty is sort of like breaking encryption and learning intelligence from communications, as opposed to the CIA, which is a different kind of spy agency. Now you might say, oh, I took a crypto course, and doesn't SSL have this like forward secrecy property that would stop that? So this is only for those of you who've done crypto before. And the answer is it doesn't help you in this case. It sort of helps you, it sort of half helps you. So this property is designed around what happens if I steal your key. So let's say you're one of the endpoints on this encrypted tunnel. You have this key, and we're going to get there, like what it's used for and things like that. But if I can steal the key, then I'm you, essentially. And so what for secrecy means is if I steal your key today, I can impersonate you going forward, so I can read all your traffic going forward, but I'm not able to decrypt your past traffic. Okay, so I can't figure out what was sent in the past with that key by getting that specific key, which is your long-term key, which is used for signatures. But there's other keys that are involved in SSL, and if you can get those keys, they're called session keys, then you could decrypt past communication. So anyways, there's a bit of technicality, but it's not a contradiction to say that there's certain parts of SSL that if you break them, you can get past information if you have a record of the ciphertext written down. Okay, so what we would do is we can put this all into an attack tree. So that's the goal. So remember, this is just one of the three main approaches, but it's recover partial data from external observation. And then we could think about, okay, what's all the stuff that doesn't go over HTTPS just based on how HTTPS works, okay? So there's all the stuff that's in the headers of the packets, which includes the routing information, which includes the domain. There's your DNS query, which also would give you the domain. And then if there's mixed in HTTP content, you might be able to read that or modify it. And then you could you could try to modify the content, not just read it, but like be an active adversary. So if you saw JavaScript go across and you modified it, then you could figure out what was going on in the website. That doesn't work because browsers block it, but it's a threat, not an attack in that case. But this is actually a threat tree, not an attack tree, so we put it in the tree anyways. Then the fingerprinting attack, so like the length of stuff and the number of resources and things like that, that's also not hidden by the protocol. So if you can use that to figure out what website someone's using, then you could achieve your goal. And then you could just store it and hope to break it in 20, 30 years. So that's another kind of attack. Okay, so the attack tree just kind of puts all these attacks together. Some of them look closer to others. So that's why they're closer in the tree. Like if I learned the domain name from DNS or from looking at the packet header, that's kind of the same attack. It's technically a different attack, but much of the path of that attack is the same. Okay, so now what we can do is we can move on to the next big sort of class of attacks. So we tried to inspect from outside the tunnel. We found that we were able to find some attacks that work. Then the next thing we could do is we could try to break into the tunnel itself. Okay, so the tunnel is protected by cryptography. If we can break the cryptography, then we can break into the tunnel. But there might be other things we can do that isn't breaking cryptography specifically that we can look at. Okay, so the idea here is that you want to break or somehow subvert the cryptography that's being used. And so I want to start by simplifying the cryptography for you. So in cryptography, what happens is you have these keys. And keys are like passwords, they're just longer and more random. You can't memorize them, you write them down. And basically, if I can get your key, I can break your communication. Okay, so the goal, I'm going to rephrase the goal as sort of getting the key, or at least that's one path to attacking it. Okay, I could try to break the cryptography without the key because there's a weakness in the encryption. But the types of encryption that show up in TLS, they tend to be like things that have been studied for 20, 30 years, and there's no known attacks on them. Okay, so there's basically no attack directly on the cryptography itself. It might be that the key they used was too small, or there's some roundabout way, there's something that's more complicated happening where I'm trying to, like the crypto's not doing exactly what you want it to do. So I'm not breaking it, I'm just exploiting the fact that it's not perfectly hiding all the information that it should hide. So I'll give you lots of stories about this. Okay, so we could try to steal the key, or we could try to actually break the crypto without the key. We're probably not going to break the crypto itself, but we might be able to break the bigger protocol. Or the other big thing is how it's implemented. Okay, so cryptography has to be turned into software. And if the translation from the math that's written down in a paper to software isn't exactly the same, right, then we could exploit that as well. Okay, so implementations of cryptography are also fair game. Or sometimes the math doesn't tell you how to do things. Okay, so one example of something that gets lost when you try to implement cryptography is like the exact protocol. Like, okay, so one thing that's really not covered is you'll have some math that's written down and it's like, okay, take this value and raise it to the power of this other value, mod this other value, and so you just do that computation, okay? You do it any way you want using any math libraries that you have, okay? The problem is one of those values is your secret, okay? Now, everyone has a different secret, okay? Let's say that my secret as a math value, as a number, it just happens to be a small number, okay? So I'm allowed to pick any number in this range, and I happen to get one that's a small value, and you happen to get one that's a big value, okay? Or my value, when it's converted to binary, it has a lot of ones in it, and yours has a lot of zeros, okay? Now that algorithm of taking something and raising it to the power of something else, to the secret, is it going to run for the exact same amount of time if my number is small and your number is bigger? Is yours going to run a little bit longer because your number is a bit bigger, right? Or because I'm looking at the binary somehow, yours has a lot of ones, so you have to do a couple extra operations. I can shortcut them because I have a lot of zeros, okay? So there's all sorts of stuff in math that if you look at the value itself, there's little shortcuts that you can take. You can do things a little bit faster depending on the value that you're given. You have an even number, I have a prime number, right? You can do yours faster or something like that. And computers are also really good at finding those optimizations. And even if you don't know them yourself, your compiler might know, right? So you type out what you want to do in code, you press enter, it compiles, and the compiler, the person who wrote the compiler, they know about all these tricks, and so they put all these tricks in, okay? But now you have a problem because the amount of time it's taken depends on the secret value. So if I can just sit back and get you to use your secret value, like say I ask you to encrypt 1,000 things, and I start a stopwatch, and I just look and see how long it takes, I might be able to start guessing what your secret value is just based on the amount of time that you're taking as opposed to someone else, okay? So in general, we call this kind of attack a side channel analysis because you're not using like what's in the protocol itself. It's something that you're looking at on the side, okay? And side channel, forget about SSL, it's like, it exists in everything, okay? It's like one of the biggest security attack surfaces for like all sorts of different protocols. So it does show up in crypto. When it shows up in crypto, it's usually based on time. So the amount of time that something takes, you can infer how much it is. So now what cryptographers do, like if you use OpenSSL, for example, which is an implementation of SSL, every single operation takes exactly the same amount of time regardless of what the key value is. There are no shortcuts. The shortcuts are scrubbed out manually by hand, and they have people that go through every algorithm making sure that like you never optimize based on the key value, okay? And so it's fixed time, it runs in constant time, it doesn't matter what the values are. So everything is like hand-tuned, but it wasn't always the case. So there's earlier examples of RSA where in a realistic setting, there's also a lot of noise. Like if I'm asking you to encrypt something and then you're responding, there's like the network noise and the delay and stuff like that. But despite all of that noise, I was still able to like basically figure out your RSA decryption key. Like the differences in time were that great that you were able to do it. Other kinds of attacks, they only work in laboratory settings. Like if you have a LAN directly between two computers, you throw them on the wild internet, it might not work because there's too much noise. But anyways, other examples, this doesn't have to do with our attack tree, but just for your interest. Other examples of side channel analysis is the amount of power that something draws. So you could imagine like an ATM. And what you could do is, let's say you could see where it was plugged into the wall. You might have a device like a voltmeter, and you plug that into the wall first, then you plug the ATM back in, and you walk away. People will go up, they'll use it, and they'll type their PIN in. And when they hit the number 3, the voltage draw is just slightly different than if they press the number 2 because the resistance on the buttons are slightly different. Okay? But you have a really sensitive voltmeter, you can tell that difference. Right, so you can just look at it and you could say, oh, they pressed 2, 3, 1, 4, right? Just by reading it off. Other things are like, things emit electromagnetic interference, EMI. So there was an example of a voting system where someone they had a radio that was really sensitive so they could hear the like kind of the noise from the voting machine. And if they voted for Alice, they would press one button. If they voted for Bob, they would press another button. And you could tell the difference. It would make like a slightly different buzzing sound depending on which button they press. So they could stand outside the polling place. They see you walking into the booth and about to vote. And then they just listen on their radio and they can tell how you voted. Sound is another one. So a lot of older computers, like when I was growing up, there's all these like weird like clicking sounds. Like computers used to be like really loud. Like they would be like these like sounds, yeah, like clicking and kind of hissing sounds and things like that. It turns out that's like computation, right? Like it's making those sounds for reasons. And so if you ask something to like say use RSA and encrypt, right? It's going to make this crackling noise. And if you change the key to something else, the crackling will be slightly different. And if you have a sensitive microphone and you can pick up the differences, you can actually read like the RSA key out of like that crackling noise. So actually the S in RSA, Adi Shamir, he gave a talk once that I went to, and he did that experiment himself. So yeah. Gyroscope's another thing. So all phones are very sensitive. Like if I rotate my screen, it knows to rotate. And you have compasses and maps, it knows like what direction. So the gyroscope is like really sensitive. And it's so sensitive that when you type, you're slightly rocking your phone. And if I reach over to type a letter over here, I kind of move it slightly different than here. You can read out what someone's typing just by looking at the motion of the gyroscope. Okay, so that's another side channel attack. Another thing is like reflection. So like if you had a camera in the back and you can't see my screen, but you can see my glasses, and the reflection of my screen is in my glasses, right? You could like figure out, like if you had a high sensitive camera, you could do that and then undo the like optical reflections and things like that and read it. So those are sometimes called tempest attacks. But yeah, question? Yeah. What if someone's walking and... Yeah, sure. So that would go under noise. So like there's always a bit of noise in terms of the measurement that you get. And then these algorithms are never 100%. They're 90% accurate. So then if they're walking, it might go from 90 to 75 or something like that. So you're always guessing. You always have some chance of being wrong. But they work. They're better than a random guess, we'll say. Yeah. Okay, so anyway, so side channel analysis is one way that you might steal a key, even if all the other, like there's no problem with SSL itself. It's just that key has to be on the server. It has to be in memory because they're using it. Every time they set up a tunnel, they have to use that key. Okay, so it has to be sitting there in order for it to be used. And if it's a website and there's 1,000 users every second, it's using that key 1,000 times a second, right? So it's fresh, it's in memory. And so so you have a chance of attacking it. Another attack is called Heartbleed. So this is a very specific attack that happened. This is an implementation flaw, and specifically it's an implementation in what's called OpenSSL. So OpenSSL it still is a very common library for implementing the SSL protocol. So what would happen is, let's say you want to put a website up. So you have to buy a server, so that's fine. So now you have your server. Then you have to choose an operating system that you want to run, okay? And you could use Windows, or you could use a free operating system that's based on Linux called Apache, okay? And because it's free and it's open source, lots and lots of people use it, more than like people would use Linux on their personal computers. Because usually if you're setting up a server, you're already kind of technically sophisticated. And so Apache is estimated to be on about 40 to 60% of major websites. Okay. Then now you have Apache running and you're like, oh, I've heard about this SSL thing. We should do that. So then you just press a button. You just say, Apache, I want HTTPS. And it says, fine, I know what that is. I have a library. It's called OpenSSL. I'll turn that on by default. You're free to use a different library if you want. Right, you can go and get something, Rapid SSL or something like that. But by default, you'll just get it. It's one click away. You can just turn it on. And so that's what happened. So a lot of people were running Apache. They were running OpenSSL because it's the default client. And then OpenSSL had this weird protocol that was put into the protocol very early on. And then I think people just kind of forgot that it was there. But it was always there. It was never turned off. And it's called the Heartbeat protocol. And the idea of the Heartbeat was just, basically, it's sort of for like debugging purposes. So there's a server and you just want to make sure that it's working right. It has OpenSSL, it's running, there's no problems in the process and things like that. So this is a simplification, but basically what you do is you walk up to it and you say, here's a message, A, B, C, D, E, F, G, repeat it back to me. Okay, so I'm going to send you a message, you just send it back to me, and then I'll know that you're running. Okay, so it's called a Heartbeat. It's just like you sort of ping the server. And then to save time and space, you can say, actually, you don't have to repeat the whole message. Just tell me the first 5 bytes of it, and then that's good enough. Okay, so that's basically what this protocol was, and it was there. No one really used it. Everyone forgot about it. And then someone realized that there was a vulnerability. So you might have a guess. When it's this simplified, you might actually guess what the vulnerability is. But let's say that instead of saying, here's A, B, C, D, E, F, G, repeat back the first 5 bytes, you say, repeat back the first 10,000 bytes or 1,000 bytes. Okay? So then the server is going to say, okay, A, B, C, D, E, F, G, that's 9, but you want 1,000. So what happens? So it's going to depend on how it's implemented. What it should do is throw an error or something and say, okay, that's out of bounds. Sorry, let's try again. but there was a vulnerability here, and so it just kept going. So it just kept repeating back. Now, what does that mean to keep going? What does it mean to keep going? What is it sending back?
The block memory.
Okay. So this value that you gave to it, it put into RAM. So it's reading it back from RAM. So it just points at the start of A, B, C, D, F, G in RAM, and then it just moves ahead 5 bytes, 7 bytes, 9 bytes, 1,000 bytes. So whatever's beside it in RAM, that comes back. Okay? And RAM is a stack, so like it's sort of last in, first out. It's the stuff that was the most recent things that it put into RAM. What's the kind of things that a server would put into RAM? What would it have lying around in RAM?
Session things.
Okay.
Password.
So session stuff for other users who are connected to the website recently, the most recent users. Okay. So what's session stuff? So passwords. Okay, passwords, tokens, cookies, keys, session keys. So these tunnel keys, the individual keys it has between users, that would be there. The data itself. So let's say it was like the tax revenue agency, like someone's like PDF that they just uploaded or whatever. Like that's the kind of stuff that's here. The point is it's sensitive personal data. Okay, so usernames, passwords, cookies, data from other users, it's all sitting there. And so this was a big problem. Okay, you could basically walk up to any server and say, give me, there's an upper limit on it. I forget. I have it. I thought I had it in the slides, but it's here. Up to 64 KB. So that's how big the buffer could be. So you could ask, that's quite a bit of data that you could get from it. Okay. Now there was one thing that people were interested in, which is, could you steal someone's what we call the long-term TLS key? So we haven't explained the crypto fully, but if you're a website and you want to do TLS or HTTPS, you have this key, and you're going to use that key for every single tunnel. Okay? Because you're using it for every single tunnel, it's basically the very first thing you load into RAM. So you boot up your computer, you put that key into RAM because the very first user that comes to you, you got to use that key. And so it's always like really deep into RAM. So the theory was that you couldn't use Heartbleed to steal this key because once a couple users have connected to the website, then RAM fills up with other stuff. And then if you can only dump 64 KB, you can never go back far enough to get the key. And so there was actually one, I've got to put the article in. There was one, like, I think it was Cloudflare or like one of these big like tech companies. And they basically, I think they even bet money or something. And they said, basically, you're never going to steal the key from us. Like you can use Heartbleed, it's really devastating. You can do all sorts of attack, but that's the one attack that you can't do is steal this long-term key. So then what people did is they took it as a challenge, right? And so then what they figured out is they figured out a vulnerability that would crash the server, then it would reboot, and because it rebooted, then RAM is basically empty, it loads the key in, and then they hit it with Heartbleed like right away. Okay, and then they were able to demonstrate that you could use it to extract this key if you're able to reboot the server. You need an exploit that's capable of rebooting it, but it was possible. So this long-term signing key that's in these things called certificates that we'll be discussing probably next class in a lot of detail, that's also something that could be stolen with Heartbleed. So Heartbleed was like kind of national news when it happened. Like you go to CBC and for a week there was all sorts of articles about like, oh, it turns out the government is vulnerable to Heartbleed or the tax agency and things like that. And one person actually got convicted criminally because he was a student and he said he was just curious, would it work on the tax agency? And so he did it. It took him 30 seconds, but then it was in a log somewhere that he did it. And he didn't anonymize himself, and so he was ultimately he got a very lenient like sentence, but he was ultimately, I think he pled guilty to it, and he just got house arrest or something like that. But anyways, this stuff is serious, right? This is serious business. Like it's not just, oh, I read about this internet bug, let's go try it out on like the government websites. Like you have to think twice about doing that kind of thing. Okay, another kind of vulnerability. This is more like a class of vulnerability is you Okay, let me explain it this way. So let's say I connect to a website like Google and I say I want to do HTTPS. Then Google will say, okay, great. It might say, I don't know what HTTPS is. I don't have that implemented. Okay, so that's one response. It might say, oh yeah, I have HTTPS. I'm using TLS version 1.0, or I'm using SSL version 3.0. It's from 1996. I'm an old website. I haven't been updated in a while. Then my browser has to decide, okay, is that good enough? Right? Is it better to do some level of encryption even though it's old? Or should I just not do any encryption at all? Right? So my browser might say, okay, this is an old website, whatever. I know SSL 3.0, so I can talk that with the server. So then it ends up setting up SSL 3.0. Okay? So the point is that there's this negotiation that happens back and forth, and it has to be there for backwards compatibility, because when version 1.3 comes out, not every server is going to upgrade. So a bunch of them are going to be running 1.2 and 1.1, and you don't want to break the whole web saying you can't connect to any server but 1.3. Okay? So there's this negotiation that happens. And then once you establish a version of SSL, TLS that you're going to use, then you even get to pick like which encryption algorithms you're going to use. So there's a whole bunch of them. They're called cipher suites, and that's also a detail that's negotiable. Okay? So the question is, what if an adversary is in the middle and they start changing messages? So you go to Google and say, hey, I support TLS 1.3, and they change the message to, oh, I only support SSL 3.0. Then Google's like, okay, great, this person knows SSL 3.0, I also know it. Then they send back a message like, let's do SSL 3.0, and your browser doesn't know that it was changed. Your browser's thinking, oh, it's Google, they don't know 1.3, they only know 3.0, right? So that's fine, I also support 3.0. Right? And then you end up with a 3.0 connection, and then maybe there's some vulnerability in that version of the protocol that was fixed in the upgrades. Okay? So this is called a downgrade attack. So a downgrade attack is you're purposely interfering with the negotiation in hopes that you can negotiate a lower level of encryption. Okay, so the short end here is that TLS does offer some protection against this kind of attack. So when you're done this negotiation phase, you end up with these cryptographic keys that you're going to use to make your tunnel. And the very first thing you do actually is say, these are all the messages that you sent me before we had these keys. Okay, we now have these keys. Now that I have the keys, I'm going to repeat to you everything I told you, but this time I'm going to use my key with it. And I'm going to send it to you, and you're going to check whether that is what you received. And if there's any difference or discrepancy between them, then we're just going to drop the connection because it looks like someone messed with it. Okay? And SSL got really, really lucky because one of the aspects, like in order for that kind of response to work, you need message integrity. Confidentiality doesn't matter so much, but integrity matters. That because I could mess with that second message where you're comparing as well. So I could mess with your negotiation, and then I could change that second message. SSL got lucky because the thing that protects message integrity, it's called a MAC, it was never negotiable. It was always fixed in the protocol. Now it actually is, ironically. So in the latest versions, it's negotiable. But in the older versions, it was just the one thing that you couldn't negotiate. And so as long as the MAC function worked, you could always like resist these downgrade attacks. Once the protocol like started doing that. So anyways, the short end is that like SSL 2.0 and 3.0, they don't do this comparison at the end. So they're vulnerable to downgrade attacks. And then TLS 1.0 and up should not be vulnerable, but it also depends on the implementation. So if the implementation doesn't track this information, or if they don't do the comparison right, there's also the chance that there's some bug in the software, and so you can downgrade them and it's just not detected. So there have been a bunch of attacks of this nature recently, even like in the last couple of years, which were against the implementation of these things rather than the actual protocol itself. And one extreme form of encryption that you can negotiate is no encryption. There's another extreme form of encryption that you can negotiate, which is encryption that is only 40 bits long, or uses keys that are 40 bits. Now, a key that's 40 bits is something I could brute force on my laptop. Might take me a day, but I could do it on my laptop. Okay? Now, you might ask yourself, well, why is there a 40-bit key even in SSL at all? Right? Why is that even an option? And it's actually an interesting question. And the answer goes back to like the 1970s and 80s when encryption was first coming out. Academics started working on it. They started developing encryption. They started publishing it. Tech companies like Netscape started putting encryption into browsers. And governments were initially opposed to it. They said encryption is something for governments. It's not for everybody. Then the academics did it anyways. And there were a lot of threats and things like that. So then the government took a middle ground position where they said, okay, we're not going to stop you from doing encryption. That's free speech. You can do whatever you want. But we're going to treat it like a weapon. So if you write software and you use encryption and you give it to someone in another country, that's as if you handed them a missile or you gave them a hand grenade, okay? You can do that. It's possible. There are legal ways of doing it, but there's a bunch of hoops that you have to jump through in order to do it, okay? You can't just do it anyways, okay? And so where they drew the line is they said anything less than 40 bits, you can export without, so it's called export encryption because you can export it to any country and it doesn't matter. You don't have to comply with any regulations. If it's more than 40 bits, you can only give it, like for example, let's say the company like Netscape was based in the United States, you could only give it to American citizens. If you gave it to non-Americans, like Canadians, then that would be considered you giving them like military grade secrets kind of thing. So what Netscape did is they originally built two browsers, one that used 40 bits for the rest of the world and one that used 128 or whatever the standard was. It was probably more like 80 bits for Americans. But then there was like a mix-up within Netscape and the American version never got released. They accidentally gave the export version to everyone. So then everyone in the world ended up with just 40-bit encryption, including Americans themselves, even though they were entitled to stronger encryption. So that's why those legacy cipher suites are there. Then what happened is the laws changed. 1990s, Bill Clinton, they changed it. They got rid of that. And then they started putting better encryption in. They could export it everywhere. So now you can download a browser with strong encryption. But for backwards compatibility, you still have to have the old ones because maybe someone hasn't upgraded from that export version. And unfortunately, backwards compatibility is one of those things where if you go all the way back, right, then these things might still be around, right? The protocol might not allow you to actually negotiate them, but they're still there. They're still in the source code somewhere. It is reachable code. And if you can find a software bug in the code that allows these things to start being used when they shouldn't be, then it will start using it. So anyway, so that's happened. There's a number of attacks that are along those lines of some sort of exploit in the software combined with some sort of downgrading of SSL, and then it's not protected adequately, and then you can attack. So you make the tunnel really weak with the downgrade attack, and then you're able to exfiltrate the data that's going across the tunnel. Okay, one last attack, I guess. Okay, so this one's called Crime, and this is a, yeah, okay. I'll show you the attack, and then I'll show you the attack tree. So, and this attack's a little bit involved. This is the most complicated attack that I'll show you, okay? But this is the kind of thing that people think about, they write papers about, they're very convoluted kinds of attacks, okay? So here's the scenario. So this is a little bit more powerful of an adversary than the adversary we had just in our node of the root node of our attack tree. So we're going to assume that the adversary is in a man-in-the-middle position. So they're reading traffic. It's going between a server and the user, and it's going over an encrypted channel. So that's standard. But let's say the adversary, in addition, is able to, they want to attack you on a particular website. So let's say it's Google. You're logged into Google. What that means, which we'll explore later in the course, is you have a cookie value. And that cookie value is being sent with every packet that you send. You're sending this value. If I can steal your cookie value, I'm logged in as you, okay? We'll go through the details later, but just think of it like that. So it's kind of like your password. It's just that it's automatically being sent, okay? So you're on Google's website, you're browsing, your cookie is part of the information that's going across this encrypted channel. That doesn't matter, it's SSL, so it's protected anyways. So you should be safe to send cookie values. That's what it's designed for, even if there's an adversary in the middle. The problem with this is that the adversary also, we're going to assume, gets some malicious JavaScript that's running on the website that you're visiting. Okay, so you're on Google, there's an ad, and the adversary paid for the ad, and somehow they were able to get some JavaScript. So Google's showing you this ad, and it's actually running the adversary's JavaScript. Okay, and it could be like, if you know about this stuff, it could be in a frame. It doesn't have to. Actually, maybe that's not true. But anyways, no, it could be in a frame. Okay, whatever. So that's the whole kind of setup. For it, okay? What the adversary is trying to do is they're not trying to decrypt everything that you're sending. What they're going to do is they're just going to target that cookie value, okay? The cookie value is a nice short value. It's highly sensitive. If I steal your cookie, I steal your account. And so that's all I'm going to target. I'm not going to target everything, okay? And there's a whole bunch of attacks that follow this template. So this threat model that we set up where the adversary has JavaScript and they're listening on the wire. There's these things called beasts. There's one called Lucky 13, one called Poodle. There's biases in RC4. They all use a different flaw in cryptography that they exploit. And if you're interested in this stuff, you can do a project on it, or you can read more about it. I'm not going to cover it in the course, but this is a very standard kind of setup. Okay, the thing that we're going to exploit is something I mentioned earlier is compression. So I mentioned, why don't we compress data before we send it? Okay, so this is one of the things that could go wrong if you compress data first. Okay, so compression is in the TLS standard. So there is support for compression, but most people don't use it. There was another alternative to TLS HTTPS. It kind of sits at a different level of the stack called Speedy, SPDY. It also uses compression. And then HTTP, the protocol, like before you layer SSL on top, it also uses encryption as well. Okay. Okay, so here's the attack. What happens is, because I control JavaScript, I'm able to send any message I want to the server. Okay, so I can open a connection to the server, and whatever data I want to put in, I can put in. Okay, I'm running JavaScript, so that's something JavaScript is capable of doing. Okay, every value that I send to Google, the user's browser is going to take the user's cookie, and they're going to stick it in front of the packet in the header. Then they're going to encrypt the whole thing, and then they're going to send it off to Google. Okay, so because the browser is taking the cookie and putting it on the packet, I can't see the cookie directly just because I'm running JavaScript on the page. Okay, so I can't use JavaScript itself to steal the cookie. Okay, so I can't directly see it. Okay, but what I can see is I can see packets that are going across the wire that are encrypted, and I know the basic information. I know where it's going, and I know the size of it. That's basically what I know. And I know that the cookie value was put on the front. I just don't know what it is. And the stuff that's at the end of the packet, I chose, because I'm running the JavaScript, so I choose that type of thing. Okay? So here's the attack strategy. What I'm going to do is I'm going to guess what the cookie is. I'm going to put my guess into the body of the data that's going across. Then what's going to happen is the browser is going to take it. They're going to put the cookie on top. Okay? If my guess is good, my guess is going to match the cookie. And if my guess is bad, it's not going to match the cookie. Okay? Then I'm going to take all of that, the cookie and the request. I'm going to put it through a compression algorithm. Okay? Then I'll get a smaller representation of the data out. Then I'll put it, I being the browser, I should say. The browser is going to put it through a compression algorithm. Then they're going to put it through an encryption algorithm. Then they're going to drop it in the tunnel. It's going to go across. And I'm going to see the length. That's all I'm going to see. Okay? I'm going to see how long. Okay? What can I tell from the length? So what I can tell from the length is how well did compression work. If I send the same message all the time, it's always going to come out the same size pre-compression. And compression is deterministic. So if I compress the same message 100 times, I'm going to get the same message out the other end. Okay? Now, what I'll do is, let's say I guess E33A, and I put that in the purple stuff at the top, so where it says request, or REQ, which stands for request. Okay? So if I put that number in the request, it shares some of the bytes that's in the cookie value as well. Okay, that's what a compression algorithm looks for. It says, oh, these bytes, they're showing up in 2 places. So instead of sending it twice, I'll send it once, and I'll say just put it in this spot and put it in this spot, and that's shorter than sending it twice, kind of thing. Okay. Now, if my guess is completely wrong and it doesn't match, right? The cookie's random values, I'm guessing random values. It's not going to compress very well. Okay. And so as a result, I'm going to see a big packet. Okay, so when my guess is getting closer, the packets are going to get smaller because it's going to start compressing well. And when it's not close, they're going to be long. Okay, and so what I'll do is I'll sit there, especially if I have a stream cipher, which is down to a byte, right? Then what I'll do is I'll just guess. It's going to take like 1,000, 10,000, 100,000, I don't know. It's going to take a lot of guesses because I'm measuring like minuscule differences, right? But eventually I'm going to learn, oh, this is probably showing up in the cookie somewhere, and then I'll kind of keep that part of the cookie, and then I'll guess a bit more, and eventually I can actually pull the cookie value out with enough guesses. So this attack isn't like super great. It's sort of an unrealistic threat model that I would have a cross-site script running on a major website like Google, and I'd also be a man in the middle sniffing Google traffic. Okay, but technically that should be allowed. HTTPS should protect you against that, but it is sort of unrealistic. I need to have the secret I'm stealing be put alongside the information that I supply. Okay, so there's adversary controlled data, and there's a secret I'm trying to steal, and they have to get glued together pre-compression. Otherwise, the attack's not going to work. So there's not a lot of secrets that are like that. Okay, a cookie is one. So this works for stealing cookies, but it's not going to work generally for other stuff that you want to steal. Okay, you're only going to be able to steal. You're going to have to send a lot of packets, I'll say, and so there's a chance that I'm running a firewall or IDS or something like that, antivirus, and it just says, I don't know why this person's sending 10,000 packets. I'm just going to turn it off, right? So it creates a weird sort of network trace in order to do the attack. And then because of that, there's a lot of trial and error. It's going to take you a while to narrow down the secret, so you're only going to be able to steal things that are a couple bytes long. Okay. So anyways, all of this put together, it's not the greatest attack in the world, but it's still an attack. It works. It worked when people were doing compression the way that they were doing. And so anyways, it would go into the attack tree. Speaking of which, so this is sort of the second category of breaking into the tunnel. So we can try to attack the protocol or implementation, either downgrade attacks. Then there's a bunch of things. We talked about heartbleed. So that's like leaking the contents of RAM. Timing attacks is a side channel attack. The downgrade freak thing was the export. We didn't really talk in full detail. Then there's a whole bunch of stuff I'm not talking about, like Beast, Lucky 13, Poodle, Crime, RC4 biases. These are like crypto attacks. They all work kind of the way that Crime works. So the way I just showed you with the compression, they all sort of, not all of them, but most of them are sort of about stealing cookies when you have JavaScript and you're in the middle. So it's that sort of same threat model. But then they're using different, instead of compression and the length of packet, they might say, oh, you have to pad the packet. How much time does it take you to pad it? Or there's different like little minor differences that they're measuring in order to steal secrets out. Okay, so that's that portion of the attack tree. Is there any questions on this? Okay, great. So I'll see you all next week.